There is a moment in every great journey where the traveler crosses a threshold that cannot be uncrossed. A point where what lies behind and what lies ahead become fundamentally different environments, and the act of passing through that boundary changes the nature of the journey itself. For Voyager 2, that moment arrived on November 5th, 2018, at a distance of approximately 11 billion miles from Earth. On one side of that invisible line sat everything the sun controls: its wind, its magnetic field, its charged particles, its protective influence stretched out across billions of miles of space. On the other side sat something no scientific instrument had ever measured directly from the inside before that day: the actual interstellar medium, the ancient plasma that drifts between the stars, the environment that exists in the space our sun does not command. Voyager 2 crossed that line, and what it found on the other side was so different from what the models predicted that 5 separate teams of scientists felt compelled to publish 5 separate research papers on the exact same day, 1 year later, just to explain what they had seen. This is not a story about a mystery nobody can explain. This is a story about a boundary that physicists studying the outer solar system had spent decades theorizing about, one that a single aging spacecraft proved they had gotten meaningfully wrong. And the implications of what they got wrong reach back across those 11 billion miles of space to right here, to the shield that makes life on Earth possible, and to serious questions about how stable that shield actually is across long stretches of time. I am your name, and this is your channel. Subscribe now if you want more stories like this. We go this deep into the real science every single week. Now let us start from the beginning, because to understand what Voyager 2 found at the edge of our solar system, you first need to understand what the edge of our solar system actually is, and why getting there took 41 years of continuous flight through the dark. Most people picture the solar system ending somewhere around Pluto. That is a reasonable assumption, honestly. Pluto was the outermost known planet for decades, and nearly every diagram in every textbook and documentary tends to stop right around there. But Pluto is not the edge of the solar system in any physically meaningful sense. It orbits well within a region still thoroughly dominated by the sun. The actual boundary, the point where the sun's influence genuinely ends and something else begins, is a completely different kind of structure, and it sits vastly farther away than most people ever learn. The sun does not simply provide light and warmth. It continuously fires out a stream of charged particles called the solar wind, blasting outward in every direction at several hundred kilometers per second. That wind pushes against the surrounding galaxy and inflates an enormous bubble around our entire planetary system. That bubble is called the heliosphere. Inside it, the sun's magnetic field is in charge. Inside it, the solar wind is the dominant particle environment. Inside it, everything from Mercury to Pluto and far beyond exists inside a continuous river of material that originated in our own star. The outer skin of that bubble is called the heliopause. It is the point where the solar wind finally runs out of push and gets stopped cold by the pressure of the interstellar medium shoving back from the other side. Beyond the heliopause, there is no more solar wind. The magnetic field belongs to the galaxy, not the sun. The particles floating around no longer came from our star. The environment is fundamentally physically different from anything found inside the heliosphere. Crossing the heliopause means leaving, in a real and literal sense, the bubble our star built for us and stepping into the galaxy itself. Voyager 2 took 41 years to reach that boundary. It launched on August 20th, 1977, and its twin, Voyager 1, launched 16 days later on a faster trajectory that would eventually put it ahead in the race outward. Voyager 2 swung past Jupiter in 1979, past Saturn in 1981, then did something no other spacecraft before or since has managed. It kept going and flew past Uranus in 1986 and Neptune in 1989, completing the only up-close tour of all 4 giant planets in a single mission. After Neptune, it kept traveling outward for 3 more decades, gradually, slowing under the sun's gravity but still moving fast enough, tens of thousands of kilometers an hour, to keep making real progress toward the outer skin of the heliosphere. Along the way, it crossed another, less famous boundary first, called the termination shock, the point where the solar wind abruptly slows from supersonic to subsonic speeds as it starts to feel the resistance of interstellar space pushing back. Voyager 1 hit the termination shock in December 2004 at about 94 astronomical units from the sun. Voyager 2 hit its own termination shock in August 2007 at a notably closer 84 astronomical units. A small early clue that the heliosphere is not a perfect sphere and does not treat every direction the same way. After the termination shock came the heliosheath, the vast, turbulent outer layer of the heliosphere, still ruled by the sun, but chaotic and compressed like the churned-up water near a riverbank. Voyager 2 spent over a decade crossing that layer before it finally reached the heliopause itself. Then, on November 5th, 2018, its instruments detected the unmistakable signature of having broken through. Solar wind plasma readings dropped to essentially nothing. Galactic cosmic rays spiked sharply. The magnetic field environment changed character. In less than a single day of travel time, Voyager 2 had passed from one physical universe into an entirely different one. It became only the second spacecraft in human history to reach interstellar space. Voyager 1 had gotten there first, crossing the heliopause in August 2012 from a different direction, at a distance of about 121.6 astronomical units from the Sun. But here's where the story turns genuinely important, and why Voyager 2's crossing produced 5 simultaneous scientific papers, while Voyager 1's crossing 6 years earlier had left some of the most fundamental questions unanswered. When Voyager 1 broke through in 2012, it was doing so with a badly damaged scientific toolkit. Its plasma science instrument, the device specifically built to measure the properties of the plasma surrounding the spacecraft, had stopped functioning back in 1980, more than 3 decades before the crossing happened. Scientists still learned a great deal from Voyager 1's magnetometer and its cosmic ray detectors, but the single most direct window into what was actually happening to the plasma on both sides of the boundary simply was not available. Researchers had to infer plasma conditions indirectly, and because of that gap, some of the most basic questions about the nature of the heliopause remained genuinely uncertain for years. Voyager 2's plasma instrument was still alive. For a spacecraft pushing 41 years old, operating in one of the harshest radiation environments in the solar system, running on hardware designed in the 1970s, using less computing power than a modern calculator, this was close to miraculous. And when Voyager 2 finally arrived at the heliopause in November 2018, that instrument was ready and working. For the first time in human history, a spacecraft crossed the heliopause with a functioning plasma sensor capable of directly measuring the temperature, density, and speed of plasma on both sides of the line, in real time, as the crossing actually happened. What it measured reshaped the picture so significantly that 5 teams of researchers spent an entire year analyzing the data before they were ready to publish. The first surprise concerned the heliopause itself. For decades, theoretical models predicted the boundary between the solar, wind, and the interstellar medium would be broad and gradual, a slow transition zone where the two environments blended together over a meaningful distance, like 2 rivers slowly merging rather than colliding at a hard edge. What Voyager 2's plasma instrument actually recorded was dramatically different. The crossing happened in under a day. On November 4th, 2018, Voyager 2 was still inside the heliosheath, the outer layer of the heliosphere. By November 5th, it was in interstellar space. There was no gradual fade. It was, at the scale of the instrument's measurements, essentially a sharp line, a boundary so thin it was crossed within a single day of travel, with plasma on one side unmistakably solar, and plasma on the other side unmistakably interstellar. The paper describing this finding, published in Nature Astronomy in November 2019, placed the width of the actual transition layer at less than 0.06 astronomical units. 1 astronomical unit is roughly 93 million miles, the distance from Earth to the Sun. Less than 6% of that distance for an entire transition between 2 totally different regions of the galaxy. At the scale space physics normally operates on, where distances are measured in the billions of miles, that is an almost absurdly thin line. Interestingly, scientists who compared the 2 crossings noted that Voyager 2's exit looked far cleaner and less messy than Voyager 1's had been, giving researchers their best ever direct look at how sharp this cosmic edge really is. The second surprise concerned temperature. Models had predicted the interstellar plasma near the heliopause would be cold, quiet, and largely uniform. What the plasma instrument actually recorded was plasma noticeably hotter than expected. Scientists measured a temperature spike in the boundary region, somewhere between 30,000 and 50,000 Kelvin, as Voyager 2 crossed through, likely because the plasma gets compressed and heated right at the edge, where the 2 environments slam together. To be clear, interstellar space itself, further out, is still far colder than the environment inside the heliosphere, where solar plasma runs at temperatures near 1,000,000 degrees Celsius. But the boundary zone was warmer, messier, and less predictable than the clean, quiet void the textbooks described. And once Voyager 2 was firmly on the other side, its instruments also caught something else. The density of the surrounding plasma jumped by a factor somewhere between 20 and 50 compared to what it had been experiencing inside the heliosphere, a leap far larger than most pre-crossing models had anticipated. The third finding came from the magnetometer, in a separate Nature Astronomy paper analyzing Voyager 2's magnetic field readings straight through the crossing. In the region of the heliosheath just inside the heliopause, the instrument detected what researchers called a magnetic barrier, a zone where field intensity spikes sharply above typical heliosheath values, forming a layer of elevated magnetic pressure sitting between the bulk of the heliosphere and the boundary itself. Voyager 1's magnetometer had hinted at something like this back in 2012, but Voyager 2's crossing confirmed it far more clearly and added crucial detail about how it interacts with cosmic rays trying to push their way in from outside. Cosmic rays are some of the most energetic particles in the known universe, hurled outward by supernova explosions and other violent events happening across the galaxy, streaming through interstellar space at close to the speed of light. The heliosphere partially shields the inner solar system from them, cutting down the radiation that ultimately reaches the planets. It turns out that shielding effect is directly tied to this magnetic barrier Voyager 2 detected. The elevated magnetic pressure impedes the inward flow of cosmic rays, deflecting or slowing them before they can push deeper into the solar system. This is a real, measurable effect with real consequences for the radiation environment around Earth, and the details of exactly how it works were not correctly described by any model built before Voyager 2 flew straight through it. The fourth finding came from comparing what Voyager 2 measured against what Voyager 1 had measured 6 years earlier, and it may be the most conceptually important result of the entire mission. The two probes crossed the heliopause in different locations, heading in different directions relative to the solar system's motion through the galaxy. Voyager 1 crossed in the northern solar hemisphere, heading roughly toward the nose of the heliosphere, the direction the sun is actually moving through the galaxy, where the solar wind pushes hardest against the oncoming interstellar medium. Voyager 2 crossed in the southern hemisphere, heading more toward the flank, a different stretch of the boundary entirely. If the heliosphere were a perfectly symmetric sphere, both crossings should have found essentially identical conditions. They did not. Voyager 2 encountered a thinner boundary than Voyager 1 had, with different plasma conditions and a distinct magnetic environment. And here is the part that genuinely puzzled scientists. Both probes found the heliopause at almost the same distance from the Sun, Voyager 1 at roughly 121.6 astronomical units, Voyager 2 at roughly 119, a gap of only about 2.5 astronomical units, despite the fact that the two crossings happened 6 years apart, in opposite hemispheres, and during completely different phases of the Sun's roughly 11-year activity cycle. By the standard models, that agreement should not have happened. A more active Sun should push the boundary out further. A quieter Sun should let it drift inward. Instead, researchers at Johns Hopkins who studied both crossings openly admitted they could not fully explain why the numbers landed so close together. It suggested that the pressure from outside, from the interstellar medium itself, plays a far larger role in pinning the heliosphere's overall size than the Sun's own internal activity does. At the same time, the character of the boundary clearly differed between the two crossing points, which tells us the heliosphere is not a smooth, symmetric bubble at all. It has a shape, dictated by the direction the Sun moves through the galaxy, and by how the interstellar wind flows around it, compressed on one side, stretched out on the other, like a comet's tail pointing away from a headwind. That asymmetry matters enormously for one specific reason researchers have been chasing ever since the data was published. If the heliosphere is compressed in some directions and extended in others, then the thickness and strength of the protective shield it provides against cosmic radiation also varies depending on which direction you're measuring from. The inner solar system may not be equally shielded in every direction across the sky. The two data points from the Voyager crossings, one from the nose, one from the flank, remain the only direct from the inside measurements we have of that shape, and they are already producing models of the heliosphere that look nothing like the tidy symmetric sphere most people were taught before 2019. The fifth major finding concerned what the interstellar magnetic field is actually doing near the heliopause. For decades, physicists assumed the galactic magnetic field outside the heliosphere and the solar magnetic field inside it were largely disconnected, two separate systems meeting at the boundary with limited interaction. What both Voyager spacecraft actually found was stranger and more tangled than that. Remarkably, Voyager 2's magnetometer confirmed something Voyager 1 had already hinted at. The magnetic field just beyond the heliopause runs roughly parallel to the magnetic field inside the heliosphere, as if the two systems are quietly aligned across a boundary that was supposed to separate them completely. Nobody predicted that alignment before either spacecraft measured it directly. On top of that, the galactic magnetic field outside turned out to be stronger than expected, running 2 to 3 times the intensity that the best pre-crossing models had calculated. That stronger field exerts significantly more pressure on the heliosphere than anyone had planned for. Independent estimates built from the Voyager data suggest interstellar particles pressing in from outside may be exerting up to 10 times the pressure earlier models assumed. That is not an abstract number sitting in a physics paper somewhere. The pressure the interstellar medium exerts on the heliosphere directly determines its size and shape. A more compressed heliosphere provides somewhat less shielding to the inner solar system. Over deep geological timescales, if the Sun happens to drift through a denser or more magnetically turbulent patch of the galaxy, that bubble could shrink significantly, exposing the inner solar system, including Earth, to noticeably higher cosmic ray intensities than we experience right now. The Voyager data does not prove that this has already happened or that it will happen on any predictable timeline. But it does establish, with hard numbers instead of guesses, that the interstellar medium pushes back on our Sun far harder than the models assumed. And that changes the baseline for how stable our protective bubble really is. All 5 of these findings, the razor-sharp boundary, the surprisingly hot and dense plasma, the magnetic barrier, the strangely matched yet asymmetric heliosphere shape, and the unexpectedly strong and aligned interstellar magnetic field, were delivered to the scientific community simultaneously on November 4th, 2019, almost exactly 1 year after the crossing itself, published together as 5 separate papers in the journal Nature Astronomy, each one covering data from a different one of Voyager 2's 5 still-functioning science instruments. The simultaneous publication was completely deliberate. The findings from each instrument team were deeply interconnected, each one adding essential context to the others, and releasing them together let the wider scientific community absorb the full picture at once, instead of piecing it together over months or years from scattered papers. The reaction across the space physics community was not panic. It was something closer to a serious recalibration. NASA scientists described Voyager 2 as effectively a pathfinder, the first platform to genuinely experience the interstellar medium from the inside, rather than theorize about it from 11 billion miles away. That word is chosen carefully. There was no path before this. There were only models built from observations, taken deep inside the heliosphere and reasoning about what should logically exist on the other side. And those models, for all their mathematical sophistication, missed the sharpness of the boundary, misjudged the plasma's temperature and density, underestimated the strength of the magnetic barrier, and completely failed to anticipate how asymmetric and tangled the whole structure actually is. A pathfinder goes somewhere first and comes back with information that redraws the map. Voyager 2 is never coming back. But the information it beamed home across 11 billion miles changed nearly every map that mattered to heliophysics. Now think about what this means for the instruments Voyager 2 still has running in interstellar space right now, more than 7 years after the crossing. Reaching the heliopause was never the end of the scientific story. It was the opening of an entirely new chapter. The interstellar medium Voyager 2, entered on November 5th, 2018, is not some uniform, silent background. It has structure. It has turbulence. Its plasma shifts in density and temperature as the spacecraft continues to push through it. Compression waves triggered by solar eruptions, events powerful enough to send shock waves rippling all the way past the heliopause and out into interstellar space, have actually been detected by Voyager 2's instruments from the outside, proof that the heliosphere and the galaxy beyond it remain physically connected in ways the old static boundary models never described. The heliosphere effectively breathes, expanding and contracting in response to solar activity and to the interstellar pressure pushing in against it. Voyager 2 has been quietly recording that breathing from outside the bubble since late 2018. Every year that passes brings the spacecraft closer to the point where its power supply can no longer keep its instruments alive. Both Voyager probes run on radioisotope thermoelectric generators, essentially nuclear batteries that convert the heat from decaying plutonium into electricity, since sunlight 11 billion miles from the sun is far too weak to power anything with solar panels. That power output naturally decays over time, and the mission team at JPL has had to make increasingly difficult choices about which instruments stay on and which get shut down for good to conserve what little power remains. In recent years, engineers have even started turning off onboard heaters for individual instruments one at a time, gambling that the hardware will keep functioning even as it grows dangerously cold, just to squeeze a few more years of science out of a spacecraft that was never expected to survive this long in the first place. The plasma science instrument that made the heliopause crossing so historically complete is still operating, but it is running on a machine that loses a few watts of usable power every single year and cannot last forever. The window for direct plasma measurements from the southern interstellar medium is finite and closing. When it finally shuts, there is currently no replacement instrument on any funded, designed, or approved trajectory to take its place. NASA and other agencies have discussed concepts for a dedicated interstellar probe that could travel faster and further than Voyager ever did, potentially reaching the heliopause in a fraction of the time using a more direct trajectory and modern instruments, but no such mission has actually been built or launched, and none is expected to arrive at the boundary for decades, even if funding appeared tomorrow. What Voyager 2 crossed on November 5th, 2018, was the edge of everything our sun ever built. the edge of everything that exists within its protective reach, the edge of everything our civilization has ever physically called home. And on the other side of that edge, it found a universe hotter than expected, denser than expected, more magnetically active than predicted, pressing in harder against our solar system than any model had, calculated and bounded by a line thinner and sharper than anyone had anticipated. The textbook image of the heliosphere, a smooth, symmetric sphere fading gently into quiet interstellar space, needed to be redrawn. 5 teams of scientists published 5 papers on the very same day to begin that redrawing. And the spacecraft that made all of it possible is still out there right now, still moving deeper into interstellar space, still measuring, still transmitting, still doing exactly what it was built to do, decades before most of the scientists currently studying its data were even born. If this kind of real, verified, world-changing science is what you come here for, subscribe right now, turn on notifications, and leave a comment below with the space mystery you want us to cover next. Share this with someone who should be watching, because this is the kind of story that deserves a far bigger audience than it usually gets. Thanks for watching. Let's go deeper into one specific piece of this story, because it is the finding that most directly connects what Voyager 2 measured 11 billion miles away to questions about life right here on Earth. And it is the one that all 5 Nature astronomy papers combined touch on carefully without any single one of them fully resolving. What Voyager 2's crossing data firmly established is that the interstellar magnetic pressure pushing in on the heliosphere runs roughly 10 times greater than pre-crossing models assumed. That stronger external pressure means our bubble is being squeezed harder than expected, which means it sits somewhat smaller than earlier models claimed. This is not a crisis. The heliosphere remains more than large enough to provide substantial protection to the inner solar system today. But it does mean the models describing how much protection we actually have and how that protection might shift across geological timescales as the sun drifts through different regions of the galaxy needs serious recalibration using real numbers, numbers that only Voyager 2 was ever in a position to physically provide. That recalibration is still ongoing. Papers published since the original 2019 analysis have continued refining our understanding of the heliosphere's shape, its response to changes in solar activity, and the structure of the very local interstellar medium surrounding it, much of it still drawing on Voyager 2's continuing data stream sent home from deep inside interstellar space. Other missions have joined the effort from a distance, spacecraft. Like IBEX, and more recently NASA's newly launched IMAP mission, study the boundary of the heliosphere by detecting particles bouncing back toward Earth, rather than sitting out there directly, giving scientists a second, complementary way to map the same structure Voyager physically passed through. But nothing replaces having an actual spacecraft on the other side, still counting particles in real time. Think about what that continuity of data really represents. Since November 2018, Voyager 2 has been sending back measurements from inside the interstellar medium nearly every single day. Plasma density readings, magnetic field strength and direction, energetic particle counts from both solar and galactic sources. The spacecraft is, in a very real sense, drawing a map, not a map of geographic. Features the way a rover draws a map of a planet's surface, but a map of conditions, a record of what the space immediately surrounding our solar system is actually like as a function of distance from the heliopause, built point by point as the spacecraft physically moves deeper into it. No such map existed before November 5th, 2018. No telescope on Earth can substitute for it, and it can only continue to be drawn for as long as the spacecraft keeps operating. Both Voyager 1 and Voyager 2 arrived at the heliopause at almost exactly the same distance from the Sun, despite crossing years apart from different directions during opposite phases of the solar cycle. Scientists genuinely did not expect that agreement. It suggests the interstellar medium's pressure is stable enough over the relevant stretch of time to hold the heliopause at roughly the same location, no matter where the Sun happens to be in its own activity cycle. The external environment, in other words, may be more dominant in setting the heliosphere's size than the Sun's own internal output alone. The galaxy presses back, and it presses with enough consistency to keep our boundary nearly fixed in place. There is something worth sitting with in that image. Our Sun doing its steady best to maintain its bubble against the constant external pressure of the galaxy, pushing in from every direction, and the galaxy holding that boundary nearly steady no matter what the Sun does internally. It describes a relationship between our star and its gallic, tick surroundings that our models had gotten wrong, one that a 41-year-old spacecraft, built on hardware that predates home computers, measured directly for the very first time on a November afternoon in 2018. That spacecraft is farther from Earth today than it was then. Its power supply is smaller, its instrument count is lower, but its remaining instruments are still collecting data from inside the interstellar medium, still extending the map that begins at the heliopause crossing and reaches outward into space. No model has ever correctly described from first principles. and that no mission besides Voyager 2 itself has ever measured directly from within. Subscribe now if you want to keep following the story. Drop a comment telling us which discovery from this video surprised you the most. And share this with someone who should know that the most important scientific data about the edge of our solar system is being collected right now by a machine built before most of the people watching this video were even born. Thanks for watching.